Related rates is probably one of the topics that students like the least in AP Calculus. Hopefully you're different. I feel the reason students don't like them is they're applied problems, and there's multi-steps. And you have to read the problem carefully and know what to do. It's not like you're following an example from 5 other problems that somebody else showed you. The AP Classroom has some wonderful videos really breaking it down, and I wanted you to start with understanding the units. And because if you understand the units in a related rate problem, I think it makes the problem less confusing. So a related rates problem is talking about how variables, 2 or more variables, are related, and it's always in respect to time. So I always suggest draw and label in a diagram if you can. You have to come up with an algebraic relationship. So if you're talking about area of a circle, its area equals pi r squared. So the variables are area and radius. Make a relationship with the 2 variables involving the rate to be determined. So you're looking for the derivative with respect to time for both sides of the equation. Solve for the desired rate and make numerical substitutions. So I'm going to start out with a couple easy examples. And then they do get a lot harder from here. These notes don't have as many examples, but the AP Classroom has a lot more. So in this case, I have the equation y equals 3x squared minus 4x. So if I draw and label a diagram, 3x squared minus 4x is going to look like this. I know it's going to pass through 0, 0. Let's see, show you where I get that. So x equals 0 and x equals 4/3. So if this is 1, this would be 4/3. And I don't need that right now. I'm just relating that to information that you're already aware of from Algebra 1, Algebra 2, Math Analysis. So now I want to find dy dt. And it's important that you know that I also have dx dt. So this is not implicit differentiation with respect to x. So I'm going to take the derivative of y with respect to t. So I have dy dt is equal to power rule 6x, but then I have dx dt. Then I have minus 4 dx dt. I can factor this out if I want to. You don't have to. I have 6x minus 4 dx dt. It's really your preference, whatever you feel like doing. I don't feel there's an advantage to one or the other. Then I want to find dy dt. Well, I'm given x is equal to 5. And I'm given dx dt equals 2. So dy dt, 30 minus 2, or 30 times 2 is 60, minus 8 is going to be 52. This does not have units because I did not apply units to the equation. But what I'm looking at is when x equals 5. So 5 doesn't even show up on here. 5 would be way up here. If I were to zoom out a lot for this, say 5 was right here, dy dt is changing 52 units of horizontal or vertical distance over time. Which makes sense, and this is one thing I like to think about, is this is increasing, so it's going to be a positive derivative. Here's another equation. xy equals 6. If I were to graph this, and you would probably be more familiar if I change this to y equals 6 over x, it's a rational function. It looks like this. So when I'm thinking about this, I want to know when x equals 3. Well, x equals 3 is over in the first quadrant. This function is decreasing. So I definitely should get a negative number. So I could take the derivative of y equals 6 over x. I'm going to go ahead and just do the equations that they gave me. So it's a product rule. So I've got the first times the derivative of the second plus the second times the derivative of the first, and the derivative is a constant is 0. I can rearrange this if I want to. You don't need to. I'm not sure if there's an advantage. I would usually rearrange it, but if I rearrange it and make a mistake in my rearranging, I'm going to have a mistake all along. So I'm just going to go ahead and plug everything. So x is equal to 3, dy dt is equal to 4. Well, it doesn't give me y, and I need that. I need to find dx dt. It doesn't give me y. So what I need to do is I need to go back up here. If xy equals 6, I know x is equal to 3, and I could solve for y. So sometimes every bit of information you need is not apparent. You might have to find it. So I'm going to have 2 dx dt equals 0. So I have 2 dx dt equals negative 12. Divide by 2, I get dx dt is equal to negative 6. Once again, I don't have units because I wasn't assigned any units in the problem. And when I said this, when I first graphed this, I said, oh yeah, okay, this function is decreasing, so the change, the derivative, should be a negative number, and it is. Okay. Here's a different type of problem. And these I got, they're very similar to ones that are in the textbook, but the AP Classroom, and we'll practice more that are very similar to ones you'd see on the AP test. So I have a point moving along a graph of the function y equals the square root of x plus 3. So first thing I'm going to do is graph y equals the square root of x plus 3. From Algebra 2, math analysis, I know that that's the functions the square root of x moved left 3. I want to find dy dt, and I'm given x is 6, and it should actually give units. This is centimeters. And dx dt is 2 centimeters per second. So I knew x was centimeters because dx is centimeters, dt is seconds. So I'm going to rewrite this as y equals x plus 3 to the 1/2. I need dy dt, so I'm going to differentiate this. So dy dt, use the chain rule. So 1/2 x plus 3 to the negative 1/2, and the derivative of x plus 3 is 1. But I have dx, it's not just 1, it's 1 dx dt. I almost forgot that. I'm going to rewrite this. I'm going to put this as 2 square root of x plus 3, because when I'm inputting numbers, it's a little bit easier for me to think of it that way. And then I have times dx dt. Now I know x is 6 centimeters. And dx dt is 2. So what I've got in units, let's spread this out a little bit. This is going to be 6 centimeters down here, and this is going to be 2 centimeters per second. My centimeters are going to cross out, which doesn't make, oh, I know why. This is going to be square root of 7. Let's forget the units for this problem for right now. Let's just leave it like this. So if I'm moving, this position is moving in centimeters per second, the y value is also going to be centimeters, and the change of y is going to be centimeters per second. So this is going to give me 6 plus 3 is 9. The square root of 9 is 3. So that means dy dt, 2's cancel out, is going to give me 1/3 centimeters per second. And I look back at the graph, that makes sense. This is increasing in the y direction a lot faster than it's increasing, or it's increasing in the x direction a lot faster than it's increasing in the y direction. So if this was, I go right 1, this would be up 1. If I go right 4, I go up 2. So this has increased 4 units and it has only gone up 2 units. One more example. I've not seen one like this on the AP test, at least recently. I've seen these are in your textbook, but your textbook is not geared for AP test. So that's why this example is here. I'm not even sure you're going to practice these ones. I think I'm going to focus mostly on what you're going to be seeing on the AP test. So once again, I'm given an equation, y equals x squared minus 3x. I'm going to graph that. It's not hard for me to graph. If I were to factor this, I know it goes through the x-axis at 0 and at 3. That's where I got the graph. I want to find the rate of change. So right away it says rate of change. I know I find a derivative of the distance between the origin and a moving point on the graph. Well, think of it this way. If I have a point moving along this graph, say I put the point right here. This is the point x1, y1. This distance here, I could use the distance formula. So I'd have the change in y, change of x. So my distance formula is going to be the square root change of x squared plus change of y squared. Well, if it's from the origin, this change of x is just going to be this x1. So I'm just going to change it to x squared plus y squared. They gave me the formula for y in respect to x. So I know y is a function of x, so I can change this y to this x squared minus 3x. I think this is one of the reasons students don't like this problem. There's a lot going on. You get lost in what you're doing and forget what you're trying to accomplish. So x squared plus x to the 4th minus 6x cubed plus 9x squared. So my distance is going to be x to the 4th minus 6x cubed plus 10x squared. And I'm just going to rewrite this as a rational exponent. Makes it a lot easier for me to think of my derivative when I have an exponent as fraction rather than square root. So now I want to take the derivative of the distance with respect to time. So instead of writing out the word distance now, I'm going to say d, and then you could use a capital D, dt. I need to use a chain rule. The derivative of what's inside here would be 4x cubed dx dt, negative 18x squared dx dt, plus 20x dx dt. So I'm just going to write it as this, 4x cubed minus 18x squared plus 20x, all of that times dx dt. It saves me writing dx dt over and over and over again. So d dt is going to equal, notice this 1/2 here for 18 and 20. If I multiply 1/2 and distribute it in, I'm going to get 2x cubed minus 9x squared plus 10x over the square root x to the 4th minus 6x cubed plus 10x squared. And that's the square root. And then don't forget dx dt. Okay, find the rate of change of the distance between the origin and a moving point on the graph. It doesn't tell me where the point is. Oh wait, no, here it does. If dx dt equals 3 centimeters per second. So I don't have a specific point. If I had a specific point, I could plug in my x values, but I don't have that. So all I'm looking for here is I'm going to type in 3 centimeters per second for dx dt. And I just like to keep it out front. I don't need to distribute. And this is going to be, the units will be centimeters per second. So now, whatever point I wanted to use, I could find the distance, how it's changing with respect to the origin for whatever x value I would have. And that would be my answer. So if you look back at it and you think about it, I would have, by the time I got here, I would have forgotten what I was looking for because there was so much algebra involved. And I think that's one of the problems with related rates problems. So hopefully this helps. I will assign some out of the books, but we will do a lot with, there's a lot on Delta Math and AP Classroom.